this tablet useful. So this time, let's talk about the connection between our defined prefix memorization. So this is a number of consecutive word match from the cut in which you see in a lot of memorization paper, the connection between this and lots of other famous metrics. So, for example, edit distance and correction. Or let's say 0-1 loss, 0-1 loss, and maybe Hamming distance, least common subsequence. So these are the metrics as very famous in traditional string processing or maybe word processing algorithm, and also some of the new novel things like n-grams ROG, which as the computer gets better, we will be able to compute these and maybe use this as a loss function, so there's some simple math that connects them and compares them. I'm not. I've seen some of the not much people mention that the connection between and pre, and actually we can construct something, but I don't want to reinvent this, because this is not really something hard. Most of them are just one-step proof, or maybe two-step proof that we can derive. So the first thing we consider is that if we want to compare two lists of words, so maybe there's a two lists of words up to some lists, so let's say big N, and I don't care about whether what happens follows. I just care about comparing the strings up to the nth unit. The first thing I can do, of course, I can use the n-pre to do it, but I can define the correction at j. CG. This is in general. This CG does not depend on what you give to the model anymore. This CG is just correctness at j. So if the two strings are the same, then it's 0. 0 if S1j is equal to S2j, and 1 otherwise. And you come up to n, you can define something like I forgot if this is called the Hamming distance or not. So you could sum up Cj, and the Cj is actually the 0-1 loss at j, which is not surprising. But also, and you could see if I ignore this part, then actually sum of Cj is a distance. So this is a distance. What do you mean this thing is a distance? So distance in the function should in a metric space should follow three things. If you can remember from maybe topology, and this is the definition that distance equal to 0 implies even if a string 1 is equal to a string 2, of course this thing we just care about up to n. So this is as a string 1 up to n equals to string 2 up to n, and also the distance. So ds1 s2 plus ds2 s3 is greater than greater or equal to ds1 s3. So this is called triangular inequality. Doesn't have to be Euclidean, but anything like any distance function should follow this. And d greater than 0 if of course s1 is not equal to s2. Let's relabel this, and oh yeah, and there's actually symmetry. Uh, the distance between the distance from S1 to S2 is equal to the distance from S2 equals to S1. And we could say that Cj follows this idea, but actually if you time it by any weight vector, Wj Cj, and it will also be this will also be a distance, right? But of course, this is you have to restrict W greater than 0, otherwise it will break down. How do you prove it? Well, the Cj is of course symmetric and d plus 0, so this comes from a product space, and it's fine. And we can actually define something like W to the power of minus j Cj. This is as dW. So this is my definition, and definition. So this will be dy. Will be this. Of course, Cj is S1j, S2j. This is a function of comparing these two. So if these are different, then the Cj is 1. If these are the same, then the distance is 0. Of course, by distance I mean Levenshtein distance, or edit distance is also a distance, but it's not defined like that. But it's also a distance, so it also follows the axiom, or these properties hold. And but I want to compare this to the classical thing. So the first thing I have is that I want to, so this is restricted to n, less than the first, the length of, so let's call n1 the length, let's call the length of the first vector n1 and length of the second vector n2, and let's restrict to the n we care to that. And what do we have? So basically, how do you compare the prefix length? So maximum prefix length. So prefix length means that for these two strings, the prefix are the same up to this n-pre. And the n-pre is the n-pre has to be smaller than maximum max length of shared n-grams, right? Why? Because the n-pre, the shared prefix n-gram belongs to all the n-grams. So if this is one probably, if this happens to be n-pre, then there at least you have this value as the maximum length of the shared n-gram. And this is in algorithm there's some pretty efficient way to compute it. We're not gonna cover that. Maybe it's called the hashing or something. I forgot. But yeah, not sure about this. So shared n-gram means maybe these four are the same as these four, so these are shared n-gram. So the word like this is 2, 3, 4, 5, and this is also 2, 3, 4, 5 doesn't have to be in the same space. And maximum length of shared n-gram is less than the largest common subsequence. What is largest common subsequence? Largest common subsequence is the shared common subsequence means there's a increment. There's a two set of values with shared with increasing with increasing index, that the pairwise value are shared. So what does it mean? So this could be 20345, 2345, and 2345 is a sequence, subsequence, and 2345 is another subsequence. And the n-gram has to be continuous. The largest common subsequence doesn't have to be continuous. So of course this is stricter. This set is smaller than this set. So of course the maximum is gonna be larger. And but how does it relate to edit distance? The thing is, the edit distance, or maybe we call it Levenshtein, is the number of steps needed to edit string 1 to string 2. So what is it? By deletion and addition. So by deleting one block of word, by deleting one word and by adding one word, that's just the Levenshtein distance. And it's good. It's useful for detecting misspelling in the searching and other things. So and how does this one relate to largest common subsequence? Well, not the largest common subsequence, but maximum length of shared n-gram. So we can call this n-max, right? So so for example, the maximum shared n-gram is this for the pair. So 2, 3, 4, 5. This is 3, 4, 5. 3, 4, 5, and then you can define a way to edit this one to this one to this. So you first delete everything else. So delete everything else. So this will be n minus n max steps to delete it to this, and then you take this one, move it here, and then you add the rest. So this will be n minus n max again. And I think if you replace that to n1 and n2 for non-restricted string, that also works. So this is how this thing connects to the Levenshtein distance. Because editing you can always find the largest edit this to the largest subsequence and put the largest subsequence and expand to the second set in a given range of steps. So this can compare largest shared n-gram with de-Levenshtein, because this is one way of editing from one string to the other string. So sorry, I forgot to add the minimum number of steps to edit by this. So this is one way of editing. So the minimum steps editing should be always less or equal to the step incurred by this process. So we get a nice inequality between Levenshtein and the largest shared subsequence. Which is not surprising. Anyway, and of course you can also calculate the probability, but it's not covered in our research. This thing, by the way, all of the inequalities in this is covered in the appendix. So if you want to look at it, we gave a simple formulation of this. One interesting thing is that you remember we defined the d1 to be to be 1 times Cj, and dw to be sigma w minus j Cj, and by comparing these two formulations, we have so given that still restricting to n to length n, we have the connection that the n pre s1 s2, so n pre is like shared consecutive word greater than n pre s1 prime s2 prime if and only if dw 1 2 just s1 s2 is less than dw s1 s2 prime so it's a prime for w greater than 2. Why? So recall the sum of geometric series. The sum of geometric series gives a1 1 minus r. So what does this imply? So sum of geometric sequence. What is this? So w minus j. So w minus 1 is the r, right? Sum of w minus j is a0, which is the starting term, depending on what the index is. 1 minus w minus 1. And so what happens is for w greater than 2, this sum causes something to happen. So remember that n pre wants to compare that. So this is the correction. The correction between 1 and 2 is, for example, is 0, 0, 1. So first the failure happens at this place and 0, 1, or maybe we don't care the rest. And C1 prime, 2 prime. So this is the correctness of. So this is the correctness of the S1 prime, S2 prime, 0, 0, 0, 1, 1. And we want to say if the first failure of this pair occurs before this, so n pre before n pre of this one smaller than this, then the distance of this is greater than this. Vice versa, because it's a double implementation. So what can we do is we can provide a capital C with 0, 0, 1, 0, 0, and all 0. So of course D12 will be this D small C12 will be greater than this C12 are greater or equal to this, and we have C1 prime 2 prime is we define it as this as 0, 0, 0, and starting at this n pre, every other term is 1. So we want to compare. So of course, D of C1 prime 2 prime is greater or equal to all the D D of small c 1 prime 2 prime, and this is of course smaller than this when w greater than 2, because when w greater than 2, you sum over you take the infinite sum. This does not make the digit flip in binary. Well, not in binary. In digits, not in digits, but this does not creates the infinite sum of ones does not supersede with the dominant W with the J with 1 power less. Why 2 is a critical point? Because you have 1 half plus 1/4 plus 2 to the power 3. This is equal to I guess this well, the limit is 1. This is the sum of 2 to the power minus j. This is the sum of 2 to the power minus j equals to 1 half plus 1/4 plus equals to 1. We can take w equals to 3 for convenience. So this completes the proof that n-pre is larger, means the weighted sum is smaller, and vice versa. So weighted sum is larger, means n-pre is smaller in the restricted string with length that's greater. But this does not extend when n is not restricted. Another way of thinking of this is to think about geometrically I think it's kind of similar to the control set. So the first one is 0 to 1, and you have in a binary expansion you have 0 0 0 0 0 1 and 1 0 and 1 1. Well, this is ternary, so you think about this as 1/3. So this is the case when w equals to 3, and dw is 3 to the minus j cj, and you write this number in the ternary expansion, and you see that this is 0 1 1, and you have 0 1 1 1 1 1 1 here, so along this line. And here you have 1 0 0 0 0. These two terms always have a gap. There's always have a gap. But then if every iteration of the control set is of line segment with 1/2 of the value, you create a problem because if it's 1/2 the problem, then you have this is 0, this is 1, this is 0 0, this is 0 1, and this is also 1 0, and this is 1 1. So 1 0 1 0 0 0 0 is equal to 0 1 1 1 1 1. So that creates a problem. So this is I think the geometric way of doing this. And of course, if you time it by any w greater than 1, this is I think it's less than Hamming distance. This is less than d1, but I'm not sure if it's called the Hamming distance. I have to look it up because when we derived this is not we did not look up the word. But well, not important. This is the well, it is important in some ways because you have to relate it to the ideas of classical string processing algorithms. Instead of reinventing things, we refer back to the terms that the pioneers of the last word what's already in the classical books, in statistics, in algorithm books, and in mathematics, instead of reinventing, keep reinventing the wheels over and over time. I think that's important. The final thing is the n-gram and the Rauch thing, and if you can bound the n-gram, you can bound the Rauch. And one interesting thing, I just want to point out one thing that's key to the proof is if two string has a shared n-gram of length n max, like how how many counting the replications, or assume there's, you can assume there's no replication, or you can count each replication as 2. How many number of n-gram with let's write it from a number. How many? What's the number of n-grams with length n less than n max? That is shared. What is the least number? It turns out the least number is that you just choose n max minus n plus 1. Why? Because you can almost see this from a plot, because you can always mask smaller n-grams onto the big ones. So the first one is like this, second one is like this, third one is like this. If the small n is 3, so this distance is actually n max minus n max minus n, and then but you have to count the first value. So this is where the plus 1 comes from. There's really no nothing that's weird. So yeah, I guess to finish the simple math, but hopefully useful results, and good. And of course, this n max is, remember, this n max is greater or equal to n3. Otherwise, there's no novelty in it, because basically we are trying to blend the new definition of we are trying to compare the way we quantify memorization to metrics in natural language processing, classical natural language processing, and also metrics in those more traditional algorithm stuff and string processing algorithm, because they're just to make comparison easier for you to compare all results to different papers. And also we're gonna post the code to the calculation, and you could see we can call, there's a lot of packages we can call from for this, and yeah, and hopefully it's useful for you. Yeah, thank you very much.